Hello, and thank you for joining me. Today, I'd like to discuss our work on capturing the interplay between natural gas price dynamics and the power grid. This work was done in collaboration between myself and my advisor, Dr. Jordan Kern at NC State. Natural gas is now the backbone of U.S. energy consumption across many key sectors, including power generation at 40%, heavy industry at 41%, and 60% of all residential heating demands. But natural gas is not immune to shocks to both supply and demand. Recent examples include the war in Ukraine, Winter Storm Uri in Texas in 2021, and Winter Storm Elliot in 2022. We can see from the charts on this slide how integral gas-fired generation is to the power sector. Electricity prices are very responsive to changes to the price of gas. This can be traced back to the role gas plays in satisfying electricity demand at peak times of day and seasons. While different regions of the U.S. appear insulated from events happening far away from each other, we can see that these neat lines of division fall away when looking at the network of natural gas pipelines between the states. Rightfully, much work has been done on trying to concurrently optimize both power generation and pipeline flows as decision support tools within a region or better coordination between utilities and gas companies. What this fails to account for is the scale at which one system can affect each other, for example, nationwide. Today, we present our approach to address this gap. We have developed a mechanistic optimization model that responds to daily changes in gas demand and returns prices. These prices are then fed into the power grid, which is also an optimization model. Really, it's many separate models, where the generation mix for every balancing authority for every hour is decided. The amount of gas consumed in each state, based on generator heat rates, can then be extracted and summed for the entire day and refed to the gas model. This process will iterate back and forth until changes in prices and power sector demand converge for each day. With this approach, we can simulate how shocks from extreme weather and other major events can impact both systems in decision-relevant time periods. So far, we have developed the gas model and run estimated daily demand through it, which I will review shortly. This slide shows the network topology and an example of a supply curve from one of the states that produce gas, in this case, West Virginia from the Marcellus Shale region. Both our supply curves and network topology come from the EIA's Natural Gas Market Module, a proven tool that is used in every year to deliver forecasts for gas production in the Annual Energy Outlook. For our model, nationwide market clearing conditions are simulated by assuming demand in each state is perfectly inelastic and must be met for all time periods. The model minimizes the cost of where it comes from and which pipeline it takes to satisfy that demand for all lower 48 states, giving us the cost of the next unit of gas at each state. These dual variables, as they are called, allow us to get the locational marginal price of gas at every point in our network, which is then fed to the power sector. Our philosophy is open source and publicly available data first to enable collaborations in future work. Since there is no currently publicly available daily natural gas consumption data by sector, we had to create our own. We did this by downscaling the EIA's monthly reported consumption to daily consumption using machine learning linear regression models. We can see here from the Louisiana dual price, our proxy for the Henry Hub, and the actual Henry Hub reported prices that we are onto something. The daily volatility is well captured and what we want to see. The drifts in price over time are more difficult to simulate since they indicate changes in overall production supply elasticity, something currently out of the scope of our model. This would not stop us from simulating short-term events, however, which is our ultimate goal. Now that we have a strong basis for the natural gas side, we will need to next integrate the power sector models and run the iteration scheme previously described. From there, we will calibrate based on historical weather events and then run stochastic simulations based on future climatological scenarios and possible weather realizations across the United States. Thanks for watching.